Have you ever peered into the intricate dance of gears inside a clock, maybe, or watched the fluid motion of a car engine and just marveled at the sheer ingenuity it took to bring it all to life? How does power, that invisible force, seamlessly travel from one component to the next? And how are these incredibly precise parts even conceived in the first place?
Yeah, it's fascinating stuff.
Welcome to the Deep Dive, presented by Knowledge Flow. Today, we're taking a deep plunge into the fundamental principles of machine design.
Right.
Our mission for this deep dive is to really unravel what machine design truly is, why it's absolutely crucial to almost every engineered object you interact with daily. And then we'll journey through some core mechanical systems and their individual components. We're going to explore everything from elegant power transmission systems to the beating heart of an internal combustion engine. Our goal is to give you a clear, structured, and genuinely eye-opening understanding of this complex field, revealing those aha moments.
Those connections.
Exactly. That connect the dots between, raw materials and functional marvels.
What's truly remarkable about machine design is that it's so much more than just, putting pieces together to build something.
Right. It's not just assembly.
No, not at all. It's a relentless pursuit of optimization, a continuous cycle of innovation, and an artistic blend of problem solving. The aim is always to create solutions that are not only incredibly efficient and safe, but also astonishingly cost-effective. It's the silent, often invisible force that underpins so much of our modern world.
You don't always think about it, but it's there.
Exactly. Think about it. Every time you hop into your car, use a simple kitchen blender, or even just feel the breeze from a fan, you're interacting with a testament to meticulous machine design.
True.
It represents a profound blend of scientific principles, creative thinking, and very practical, hands-on application. Today, we're going to pull back the curtain on this intricate world, exploring everything from the big picture conceptual design phase all the way down to the nitty-gritty details of how specific components, like, say, pistons and crankshafts, are painstakingly engineered to perform their vital roles.
Okay, so let's start with the absolute bedrock then, the foundational definition. At its very essence, machine design is what?
It's the deliberate process
of
arranging individual parts or components of a machine to form a coherent mechanism.
A mechanism.
And the crucial element here, the real purpose, is that this mechanism must then provide a useful output in the desired form or, to meet a very specific need. It's never just about randomly assembling parts.
Got it. Purposeful.
Absolutely.
Imagine a vehicle, for example.
Right.
Every single one of its components is intentionally designed to optimally meet all its functional requirements.
All of them.
And to do so at the lowest possible cost. It's an incredibly intentional, purpose-driven assembly where every single part has a reason for being there, a specific function to fulfill within the larger interconnected system.
And when we zoom out and connect this to the broader landscape of engineering, it becomes clear that machine design is anything but a static field.
Right. It keeps changing.
It's constantly evolving, perpetually pushing the boundaries of what's possible. It's not merely concerned with the creation of entirely new machines, like, the very first steam engine or those groundbreaking early flight systems. Crucially, it also encompasses the ongoing process of upgrading and improving existing designs. This continuous evolution is the engine, if you will, that drives all technological progress.
And that has real-world impact.
Oh, absolutely. It has a profound economic impact. Effective machine design directly translates into a significant reduction in both overall production and operational costs.
So cheaper to make, cheaper to run.
Exactly. This isn't just theoretical. It manifests in real-world efficiency and affordability, making products accessible and sustainable in the global market. To truly appreciate the breadth of this field, it helps to understand how machine design is typically categorized. There are 3 primary classifications, each demanding a distinct approach and level of innovation from the engineer.
Okay, what are they?
Firstly, we encounter adaptive design. This is perhaps the most ubiquitous form. It involves making relatively minor changes, alterations, or modifications to products that already exist.
So like refining something.
Precisely. Think of it as refinement and iteration rather than a complete overhaul. For example, when a new car model comes out with slightly improved fuel economy or a redesigned dashboard layout, that's adaptive design at play. It leverages proven concepts and makes them incrementally better or tailored to new market demands.
Makes sense. What's next?
Stepping up in complexity, we have development design. Now, this approach requires a more substantial reevaluation.
Okay.
It involves adopting a new material, perhaps lighter, stronger, or more resilient, or implementing a completely different manufacturing method to create new machines or significantly evolve existing ones.
So bigger changes than just adapting.
Much bigger. This type of design necessitates considerable scientific training and significant design aptitude as it involves fundamentally modifying existing ideas into something genuinely novel.
Can you give an example?
Sure. Consider the shift from pure mechanical calculators to early electronic ones.
Right.
Or from conventional steel structures to lightweight composite materials in aerospace. Those were development designs, integrating breakthroughs from diverse fields.
I see. And the third type?
And then, at the pinnacle of innovation, there's new design. This is the uncharted territory, the frontier of invention.
The really big leaks.
Exactly. It demands an immense amount of research, extensive technical ability, and truly groundbreaking creative thinking, because you are quite literally starting from a blank slate.
Like inventing something completely new.
Precisely. Imagine the first working internal combustion engine, or the invention of the printing press, or the very first functional computer system. These were not mere improvements, they were entirely new designs that solve problems in ways never before conceived.
Wow. Requiring fundamental scientific and engineering breakthroughs and a complete reimagining of what was technologically feasible.
Okay, so adaptive, development, and new design. Those are the classifications of what's being designed.
Correct. And beyond those classifications, machine design also employs various methods for how the design process is executed, each suited to different problem sets.
Ah, the how. Okay.
One cornerstone method is rational design. This is deeply embedded in the principles of engineering science. It's based entirely on rigorous mathematical formulae and the fundamental laws of mechanics.
So pure physics and math.
Pretty much. This is where the physics and the advanced mathematics truly come into play, providing a precise, predictable framework for how components will behave under various stresses and motions. It's about designing from first principles.
Got it. What else?
Contrasting that is empirical design, which relies heavily on empirical formulas. These formulas are often derived from extensive observation, meticulous testing, and accumulated experimentation, rather than purely theoretical calculations. So more based on experience and testing.
Exactly. It's about learning from what has demonstrably worked in the past, especially in situations where the underlying mechanics are too complex or unpredictable to model perfectly. Think of it as building upon a vast library of practical experience.
Practical wisdom, almost.
In a way, yes. Then there's industrial design, which, in this context, focuses specifically on the production aspects of a machine.
Making it manufacturable.
Precisely. This method ensures the efficient manufacturability of any machine component in a large-scale industrial setting. It's the bridge between the abstract design concept and the practical realities of bringing that design to life, often for mass production.
Asking, can we actually make this efficiently?
Exactly. Questions like, can this be manufactured efficiently? Is it cost-effective to produce at scale? Will it meet quality standards consistently? Those are the core concerns of industrial design.
Okay. What's next?
Optimum design. This aims to achieve a given objective function under specified constraints. This is where the magic of efficiency often happens.
Like maximizing performance while minimizing weight.
Perfect example. Imagine designing an aircraft component. You're trying to maximize its strength and durability while simultaneously minimizing its weight. Or you're striving for maximum power output from an engine while keeping fuel consumption to an absolute minimum. It's a sophisticated balancing act, finding the absolute best possible solution within a predefined set of limitations and trade-offs.
Like Formula One cars.
Exactly. Every gram, every milliwatt is ruthlessly optimized. That's optimum design in action.
Okay, 2 more methods.
Yes, system design takes a holistic view. It deals with complex mechanical systems as an integrated whole, like an entire motor car or a sophisticated factory assembly line.
Looking at the big picture.
Right. It involves meticulously looking at the intricate interplay of all its constituent parts, how they interact, and how each component contributes to the overall function and performance of the complete system.
Yeah.
It's about seeing the forest and the trees.
And the final one.
And finally, element design. This focuses on the individual mechanical components within a larger system. This is where the meticulous detail truly comes into play.
Down to the individual bolt almost.
Pretty much. You're designing a specific piston or a crankshaft or a connecting rod, ensuring its individual integrity and optimal performance within the broader context of the system it belongs to. Each of these components, though a small part of a larger machine, requires its own dedicated design process and microscopic attention to detail.
That's a really powerful framework for understanding the different layers of design. So, with all that in mind, what are the core considerations for engineers when they're actually, putting pencil to paper, or more likely, pixels to screen to design a specific machine component? It's far more intricate than just making sure the thing moves.
Oh, absolutely. This is where the real depth and challenge of machine design emerge.
So what's top of the list?
First and foremost is understanding load and stresses. This is absolutely fundamental. Machine components are subjected to a dizzying array of forces.
Like tension, compression.
Exactly. They might experience tension, where something is being pulled apart, compression, where it's being squeezed, shearing, where forces are acting parallel to a surface, trying to slice it, bending, if it's acting like a loaded beam, or torsion, if it's being twisted.
A lot to consider.
A huge amount.
Right.
Designers must meticulously account for all these internal forces to ensure the part doesn't fail catastrophically under operation. It's about anticipating every push, pull, and twist.
Okay, what else?
Then there's the kinematics of the machine. This is all about the motion, how parts move relative to each other.
Straight line, curved path.
Precisely.
Yeah.
Is it rectilinear motion in a straight line? Curvilinear, following a curve? Does it need constant velocity, or does it accelerate and decelerate rapidly? Understanding these precise motion profiles is absolutely critical for achieving the desired output from the machine.
Because if one part's off,
the whole thing can fail, or just not work right, or wear out way too quickly. If a part moves incorrectly, or even slightly out of sync, the entire mechanism won't function as intended.
Right. And then materials.
Material selection. Huge. It is, without exaggeration, an entire universe unto itself. A designer must possess a profound knowledge of the myriad properties of different materials.
Like strength, weight.
We're talking about things like ultimate strengths, how much load it can bear before failing, durability, how long it will last under cyclic stress, flexibility, if it needs to bend without breaking, its weight, which can critically impact efficiency, especially in moving parts, its resistance to extreme heat and corrosion, especially in harsh operating environments, its ability to be cast, forged, or machined, its electrical conductivity, if that's a factor, and crucially, its overall behavior under the specific, often brutal working conditions. The wrong material
Can ruin a great design.
Absolutely. No matter how perfect the geometry, the wrong material can doom a design.
Okay. What about the shape and size?
Next up, the form and size of the parts. This is far from arbitrary. To precisely determine the form and size of any machine part, an engineer needs to know the exact forces that component must reliably sustain.
Not just steady forces, right?
Exactly. It's not just steady, predictable forces. They must also anticipate suddenly applied loads like an impact or shock, which can cause instantaneous failure if not properly accounted for. It's about building in robust resilience.
And friction, always a factor.
Always. Frictional resistance and lubrication are constant adversaries in machine design. There's always an unavoidable loss of power due to friction between moving surfaces, which generates unwanted heat and reduces overall efficiency.
So you need good lubrication.
Meticulous attention must be given to lubricating all surfaces that move in contact with others. Proper lubrication isn't just about preventing wear. It's key to smooth, long-lasting operation, minimizing energy waste, and preventing overheating. It's like ensuring the arteries of the machine are clear and flowing.
Makes sense. What about the user?
Good point. Convenient handling features. This consideration directly impacts the human user, and it's often what separates a merely functional machine from a truly great one.
Like where the controls are placed.
Exactly. Designers must ensure that all operational handling features, things like starting mechanisms, control levers, and stopping devices, are intuitively located and easy to use. A machine that is technically brilliant but a nightmare to operate will not succeed in the market. It's a testament to user-centric design.
Important. And using standard parts. Is that a consideration?
Very much so. The use of standard parts is a pragmatic yet powerful consideration. Whenever possible, incorporating standard components like off-the-shelf gears, pulleys, bearings, and fasteners significantly increases the efficiency of machine assembly and reduces overall manufacturing costs.
Less custom work.
Right. It also means less custom fabrication, simplifying the supply chain. For example, minimizing the variety of bolts and studs used in an assembly prevents delays caused by constantly changing tools during the manufacturing process. It's about intelligent standardization.
Okay. And safety must be huge.
Safety of operation is an absolutely critical and often legally mandated aspect of machine design. Machines, especially those operating at high speeds or under high power, can be inherently dangerous.
Moving parts are hazards.
Definitely. Any moving part of a machine that's accessible to a worker is considered a potential accident hazard and can cause severe injuries. Therefore, it is paramount that a designer always incorporates safety devices and features for the operator. This isn't just about avoiding lawsuits. It's about protecting human lives and preventing catastrophic incidents.
Critical. What about cost?
The cost of construction, the ultimate gatekeeper for any design. A high manufacturing cost can immediately bar even the most innovative and efficient machine from commercial production.
Doesn't matter how good it is if no one can afford it.
Precisely. No matter how brilliant the engineering, if it's too expensive to make, it simply won't be made. Therefore, a core aim for any design engineer is to intelligently reduce the manufacturing cost without compromising performance, durability, or safety. It's a constant, delicate balancing act between engineering perfection and economic viability.
A tough balance. Anything else?
And finally, assembling. Every machine or structure, from a simple bicycle to a massive industrial press, must be assembled as a functional unit before it can serve its purpose.
Thinking about how it all goes together.
Exactly. For very large units, it's often necessary to assemble them entirely in the workshop, conduct thorough testing to ensure everything works perfectly, and then disassemble them for transport to their final place of service where they are reassembled.
Wow, that's complex.
It is. This foresight and planning for assembly, testing, and even transportation needs to be meticulously baked into the design process from the very beginning. It's not an afterthought, it's part of the core design challenge.
That detailed list of considerations really underscores the complexity. So with all these factors swirling, how do designers systematically approach such a daunting and intricate task? Is there like a standard procedure?
There is. There's a well-defined general procedure in machine design, almost like a step-by-step roadmap that guides them through the entire process.
Okay, walk us through it. Step 1.
The very first step is the recognition of need. Before any drawing board is touched or any calculations are made, you need a complete and crystal clear statement of the problem.
The why.
Exactly. What is the aim? What is the specific purpose? What are the precise needs for which this machine is to be designed? This is the fundamental why behind the entire project. Without a clear understanding of the problem, any solution, no matter how clever, will likely miss the mark. It's about defining the target.
Makes sense. What's next?
Once that need is recognized and clearly articulated, the next step is synthesis, particularly focusing on mechanisms. This involves brainstorming and then selecting the most promising mechanisms or combinations of mechanisms that will deliver the desired motion and achieve the maximum output.
So figuring out how it will move.
Precisely. This is the how it moves part, choosing the fundamental mechanical principles that will bring the machine to life.
Then what?
Following that, there's a meticulous analysis of forces. This includes identifying all the forces that will be acting on each and every part and component of the machine, as well as understanding the precise way energy will be transmitted through them.
What pushes and pulls where?
You got it. You need to know what pushes, pulls, twists, and bends on every single element under various operating conditions.
Okay, forces analyzed, now materials.
Yes. With the forces clearly mapped out, material selection becomes paramount. This involves choosing the absolute best material for each individual part and component of the machine, specifically to manage those identified loads and stresses. The right material.
That makes all the difference.
Right. Its unique properties can make all the difference in a component's performance, durability, and safety.
Okay, material chosen, now size and shape.
Then comes the rigorous design of elements, focusing on their size and how they handle stresses. In this critical step, the exact dimensions, the size, and form of each part and component of the machine are determined.
Based on the forces and material strength.
Exactly. This is done by taking into careful consideration all the forces acting on them and the permissible stresses for the selected material. A crucial engineering principle here is ensuring that each part and component will not deflect or deform beyond permissible limits, even under peak loads.
How big and how strong it needs to be.
With very tight tolerances, yes.
Is the design final then?
Not usually. After the initial design is laid out, there's often a vital modification phase. This is where the practical experience of the engineer comes into play.
Tweaking it?
Essentially, yes. The size of components might be adjusted based on past successes, accumulated knowledge, and expert judgment, specifically to facilitate easier manufacturing and to reduce the overall cost of production. It's the tweaking for reality step, where theoretical perfection meets the practical constraints and efficiencies of the real world.
Okay, modified for reality, then drawings.
Correct. Once the design is thoroughly refined and optimized, a comprehensive, detailed drawing is produced. This involves creating precise, unambiguous drawings of each individual component and the complete assembly of the machine.
The blueprints.
Exactly. These drawings include all their complete specifications, tolerances, and instructions for the manufacturing process. These are the blueprints, the precise instructions that guide the creation of the physical product.
And the final step.
And finally, the last stage of this entire systematic process is production. This is where the component or the entire machine is manufactured in the workshop, meticulously following every detail outlined in the engineering drawings. This is the making it real part.
Bringing it to life.
Transforming the design from concept into a tangible, functional product. It's a systematic, iterative process that underpins the reliability and performance of everything we build.
That systematic approach is truly fascinating, revealing the deep thought behind everyday objects. Okay, let's pivot now from these general design principles to a specific and absolutely crucial area. How power actually moves within a machine.
Power transmission, vital.
Right, power is very rarely generated exactly where it's needed. It almost always has to travel. This is where power transmission systems step in, acting as the circulatory system for energy within a machine.
It's a good analogy.
At their core, power transmission systems are intermediate mechanisms designed to transmit power from a prime mover, like an engine or electric motor, to the actual working parts of a machine, or even from one part of a complex machine to another.
The middlemen of motion.
Kind of. And these systems are indispensable for a multitude of reasons beyond just moving power. They're critical for safety, enabling remote operation. They contribute to user convenience by allowing for flexible machine layouts, and they facilitate easier maintenance by separating power generation from power application.
Yeah, that separation is key.
Think about it. A prime mover typically provides uniform rotary motion, but the driven machine might require something entirely different. Perhaps a back-and-forth reciprocating motion, or rocking motion, or even a screw-type motion. Power transmission systems are the ingenious translators that make these conversions possible, bridging the gap between raw power and functional movement.
What's truly captivating here is the sheer diversity of these power transmission systems. Each type is uniquely suited for different applications and specific engineering constraints, offering designers a rich toolkit.
So what are the main types?
The most commonly used mechanical power transmission systems are generally classified into 4 main types. First, we have belt drives.
Okay, belts, like in a car engine.
Often, yes. These are incredibly versatile and are primarily used to transmit power from one shaft to another, especially when the center distance between those shafts is quite large. Belts themselves come in different forms.
Different types of belts.
Right. Flat belts are commonly used for moderate power transmission, often over distances up to 8 meters. V-belt drives are essential in industrial settings for transmitting much larger amounts of power, particularly when the pulleys are positioned quite close to each other. And circular belt drives are employed for transmitting power over very large distances, often exceeding 8 meters.
Okay, belts, ropes. What else?
Next, there are rope drives. These systems are widely utilized when a substantial amount of power needs to be transmitted, but the distance between the two pulleys is typically not more than 5 meters. They offer a robust and reliable solution for heavy-duty applications, often seen in older, larger machinery.
And chains.
Then we encounter chain drives. These consist of an endless chain composed of rigid links that are hinged together, providing the necessary flexibility for the chain to wrap around the driving and driven wheels. These wheels, known as sprockets.
Like on a bicycle.
Exactly like on a bicycle. Sprockets have projecting teeth that fit precisely into corresponding recesses in the chain links. The critical advantage of chain drives is that they provide positive power transmission, meaning there's absolutely no slipping between the driving and driven components.
No slip. That's key.
Absolutely. This makes them ideal where precise timing and speed ratio are non-negotiable.
Okay. Belts, ropes, chains. What's the fourth?
And finally, we have gear drives. These are essentially circular discs with precisely cut teeth on their periphery. These teeth mesh directly with corresponding recesses on their mating gears, transmitting power through direct positive contact.
Like in a gearbox.
Precisely. Gears are the go-to solution when the distance between the shafts is very small due to space limitations, and crucially, when a definite precise velocity ratio is paramount. Each of these systems represents a clever solution to a fundamental engineering challenge.
Okay, let's dive deeper into belt drives for a moment, given how common they are. You mentioned classifications based on arrangement.
Yes, how they're set up.
The most straightforward is the open belt drive. You said this is used when shafts are parallel and need to rotate in the same direction, often over a considerable center distance.
Correct.
In this setup, the driver pulley pulls the belt from its lower side and delivers it to the upper side. So, the lower side, which is under greater tension as it transmits power, is aptly called the tight side. Conversely, the upper side, with less tension, is referred to as the slack side. It's a very common and efficient configuration.
Very common.
Then there's the cross, or twist belt drive. Also for parallel shafts, but the key difference is the shafts need to rotate in opposite directions.
Right, the twist reverses the direction.
Here, too, the driver pulls the belt from one side, creating tension, while the other side carries less load. The distinctive feature is that the belts literally cross each other, forming an X shape.
Which can cause wear.
Right. This crossing means there will be some inherent wear and tear where the belt rubs against itself, which is a consideration for maintenance and belt life. So what does this tell us about selecting the right belt drive? It's not random, right? There are factors.
Absolutely not random. It's a decision driven by a multitude of factors. You need to consider the total power to be transmitted.
How much work it needs to do.
Exactly. The desired speeds of both the driving and driven shafts, the required speed reduction ratio, the physical center distance between the shafts, whether a positive drive meaning absolutely no slip is essential, the overall layout of the shafts and the available space within the machine, and finally, the specific service conditions the drive will operate under, like temperature, dust, moisture.
All those things matter.
Every single one. All these factors are weighed to make the optimal engineering choice.
Okay. And beyond those practical factors, there's the physics, right? You mentioned velocity ratio, slip.
Indeed. There are crucial physics principles that truly govern how belt drives perform and behave. First, the velocity ratio, VR. This is simply the ratio between the rotational velocities of the driven shaft and the driver shaft.
Speed out versus speed in.
Basically. Ideally, if D1 and N1 are the diameter and speed of the driver pulley, and D2 and N2 are for the driven pulley, then the velocity ratio is N2 divided by N1, which ideally equals D1 divided by D2.
Ideally.
But in reality, you must account for the thickness of the belt. So a more accurate velocity ratio becomes N2 over N1 equals D1 plus T over D2 plus T. It's a subtle but important detail for precise calculations.
Okay. Now what about slip? That seems important.
Very important. The concept of slip of belt. Ideally, when the driver pulley rotates, it carries the belt purely due to a firm frictional grip. But sometimes, especially under heavy loads or insufficient tension, this frictional grip isn't enough.
The belt slides a bit.
Exactly. This can cause the driver pulley to rotate slightly without fully carrying the belt along with it, almost like the belt is momentarily sliding backward on the pulley. This phenomenon is called slip, and it's usually expressed as a percentage.
And that affects the speed ratio.
Critically. The crucial implication is that slip reduces the effective velocity ratio of the system. This is precisely why belt drives are not used in applications where a precise, unvarying velocity ratio is of prime importance, because slip introduces an element of unpredictability.
So there's a formula for that too.
Yes. If we consider S1 as the percentage slip between the driver and the belt, and S2 as the slip between the belt and the follower, the velocity ratio with slip is then VR equals D1, D2, multiplied by 100 S1, S2, 100.
Got it. And you also mentioned creep. What's that?
Next, there's a more subtle phenomenon called creep of belt. This isn't the same as slip. Creep is caused by the elasticity of the belt material itself.
The belt stretching.
Exactly. Imagine a rubber band. As you pull on it, it stretches. When the belt passes from the looser slack side to the tighter load-carrying side, that portion of the belt actually stretches slightly due to the increased tension. Conversely, when it moves back from the tight side to the slack side, this portion contracts again. Due to these continuous, minute changes in length, there's a slight, almost imperceptible relative motion between the belt and the pulley surfaces. This relative motion is what we call creep.
So it affects speed too?
Slightly. Because of creep, the velocity of the belt is slightly lower than the driving pulley's surface speed and slightly more than the driven pulley's. While there's a formula involving stresses and Young's modulus.
Young's modulus, right? Stiffness?
Yes, a measure of its stiffness. Its effect is usually very small, typically around 1%, so for many practical applications it can be largely disregarded, though it's always present.
Okay. And one more factor, centrifugal tension.
And a final critical consideration is centrifugal tension. Imagine a small segment of the belt rapidly moving around the pulley. Like any mass rotating in a circular path, it experiences a centrifugal force, pushing it radially outward.
Trying to fly off?
Essentially, yes. When the belt runs continuously over pulleys, this centrifugal force is produced due to its own mass, and its net effect is to increase the tension in both the tight and slack sides of the belt. This additional tension, caused purely by the centrifugal force, is known as centrifugal tension.
Doesn't matter much.
Crucially, it's highly dependent on the speed of the belt. At speeds below 10 meters per second, its effect is very small and can often be safely neglected. However, at speeds exceeding 10 meters per second, its effect becomes considerable and must be rigorously accounted for in the design calculations.
Why?
To prevent excessive stress on the belt and pulleys. The formula for centrifugal tension, TC, is simply mem times v squared, where m is the mass of the belt per unit length and v is its linear velocity. This means the total tension in the tight side becomes T1 plus Tc, and in the slack side, T2 plus Tc. It adds to the overall load.
That 10 meters threshold is interesting. Okay, and pulleys are obviously part of this system.
And of course, we can't talk about belt drives without giving credit to the unsung heroes, the pulleys themselves. A pulley is essentially a wheel-shaped rotating device meticulously mounted on an axle. It's designed to support the movement and change the direction of the belt along its circumference.
Simple machines, right?
Classic simple machines that help to reduce the lifting force when used with cables or ropes, and they are absolutely fundamental in transmitting power in belt drive systems. When assembled with belts or chains, they form a system that efficiently transmits power from one rotating shaft to another. You'll find them in various types, including rope pulley systems and, of course, belt pulley systems.
Okay. And you mentioned V-belts specifically.
Yes, let's quickly touch on V-belt design. These belts, as we mentioned, are specifically engineered to transmit a large amount of power, particularly when the two pulleys are positioned very close to each other.
They have that V shape.
Right. V-belts are complex, multi-layered structures, typically made of interwoven cotton, fabric, and cords, all encapsulated within rubber and vulcanized into their characteristic trapezoidal sections. They are designed with several key sections.
Layers.
Yes, layers to handle the varied stresses they encounter. Their sophisticated internal structure allows them to carry significant tensile loads, flex efficiently around pulleys, and, crucially, transmit force through the wedging action of their side walls within the pulley groove. The standard angle for the V-belt is typically designed to be 40 degrees, which is a key factor in its wedging performance.
And the pulley for a V-belt is called a sheave.
Correct. Finally, there's the V-belt sheave, which is the specific term for the pulley designed to accommodate V-belts. These sheaves are commonly manufactured from robust materials like cast iron, fabricated steel, or various aluminum alloys.
And the fit is crucial.
Absolutely crucial. The successful and efficient application of a V-belt drive depends entirely upon the perfect, precise matching between the V-belt and the sheave's grooves. The groove design is meticulously critical. The belt should not touch the bottom of the groove.
Why not?
It's the wedging action on the sides that transmits power. Also, the top of the belt should not protrude outside the groove. When the belt is properly seated in the sheave, its top section is subjected to compression, which cleverly results in a slight reduction of the angle between the side walls of the belt. This creates that essential powerful wedging action within the groove, ensuring superior grip and power transfer.
That's incredibly detailed engineering for just a belt and pulley system.
Yeah.
Okay, so if slip is a persistent challenge with belt drives, what's the ultimate solution when you simply cannot have any slippage whatsoever?
Well, for many applications, the answer lies with chains.
Chain drives. These are known as positive drives because, unlike belts, there's absolutely no slipping between the driving and driven components.
Exactly. Positive engagement.
They transmit power between parallel shafts using an endless chain that runs over two toothed wheels called sprockets. The smaller sprocket is typically referred to as the pinion, and the bigger one is called the wheel. The chain itself is ingeniously constructed from a series of rigid links that are joined together by pin joints, providing the necessary flexibility for the chain to wrap smoothly around the sprockets. The teeth of the sprockets are precisely designed to fit into corresponding recesses in the chain links,
ensuring that completely positive non-slip engagement. These chains are usually fabricated from high-grade steel, and the critical pins and bushings within the links are precision ground to ensure accuracy of the pitch, which is vital for smooth operation and extending the chain's lifespan.
So why choose chains over belts then? What are the big advantages?
Well, when we consider the broader engineering context, the advantages of chain drives are quite compelling for specific applications.
Like the positive drive.
Firstly, yes, as you rightly pointed out, chain drives provide a positive non-slip drive. This is their paramount selling point for applications where precise timing and an exact speed ratio are non-negotiable.
Okay. What else?
Secondly, they are generally more compact than belt drives for transmitting the same amount of power, meaning they can deliver more power within a smaller physical footprint. This is invaluable in space-constrained designs.
Good point.
Thirdly, chain drives can operate effectively under adverse temperature and atmospheric pressures environments that might cause rubber or fabric belts to degrade or fail.
More robust.
Definitely. Fourth, a single chain can be ingeniously arranged to drive more than one shaft simultaneously, which can significantly simplify mechanical systems. And finally, they often require less maintenance compared to belt drives, particularly in the long run.
Fewer adjustments?
Often, yes, thereby reducing operational downtime and associated costs.
Okay. Are there different types of chains?
Yeah. Yes. When it comes to the types of chains, driving chains are generally categorized into three main types based on their construction. Number one, roller chain.
That sounds familiar.
It is. This is by far the most common and widely used type. A roller chain consists of two rows of plates. Outer plates, known as pin links or coupling links, and inner plates, known as roller links.
Okay.
Pins are securely fitted in the pin links and pass through bushings that are fitted in the roller links, joining them all together. Crucially, small rollers are mounted on these bushings, and they are designed to rotate freely on the bushings.
Why rollers?
This clever design helps to protect the sprocket teeth against wear as the chain engages and disengages. The pins themselves are also free to oscillate inside the bushings, contributing to the chain's overall flexibility.
Got it. What's the second type?
Number two is the bush chain. This is an older type of chain, less common in modern power transmission applications. They were used earlier, but are known to produce significantly more noise. Yes, when approaching or leaving the sprocket teeth due to the direct rubbing between the teeth links, which led to the decline in widespread use.
Okay. And the third?
And number three is the silent chain. Now these chains, while not truly silent, are remarkably smoother and quieter in operation compared to roller chains.
How do they manage that?
Their ingenious design incorporates a self-correcting mechanism. As a chain naturally stretches slightly over time and its pitch increases, the links are designed to ride on the teeth of the sprocket wheel at a slightly increased radius.
Compensates for wear.
Exactly. This clever mechanism automatically corrects for small changes in the pitch, maintaining smoother and quieter operation. However, silent chains are generally more complex to manufacture, more expensive up front, and typically require more meticulous maintenance due to their intricate design.
Fascinating look at chains. Okay, let's pivot now to gear drives. You call them the workhorses of precision. What exactly are gears again?
They are essentially circular discs with precisely engineered projections, or teeth, on their periphery. These teeth are designed to mesh perfectly with corresponding recesses in their mating gear.
Direct contact.
And power is transmitted by direct positive contact between those meshing teeth.
And their big strengths are small distances and positive drive.
Exactly. One of their biggest strengths is that gears are indispensable precisely when the distance between the shafts is very small, making them perfect for compact designs. And just like chains, in precision machines where a definite unvarying velocity ratio is of prime importance, gear drives are found to be most advantageous because they provide a completely positive drive with absolutely no slip.
And we see them everywhere.
Oh, absolutely. You'll find gears everywhere, often hidden but vital. They are core elements in automobiles, managing everything from engine power to wheel rotation, in heavy-duty rolling mills, in incredibly precise metal-cutting tools that shape components with micron accuracy, and in a vast array of hoisting and transmitting machinery. They are fundamental building blocks.
Let's delve into their design then, and the different types. What are the key design considerations?
Indeed. The design of gear drives demands an incredibly meticulous approach, considering several critical factors to ensure their efficiency, durability, and reliability under strenuous conditions. Key design considerations for gear drives include, first, teeth strength.
Gotta be strong.
Absolutely. The individual gear teeth must be engineered to be sufficiently strong to reliably withstand both static loads, constant pressure, and dynamic loads, forces that change rapidly, such as impact or vibration. This ensures they don't chip, crack, or break.
Okay, what else?
Wear-resisting property. The material selected for the gear teeth, along with any surface treatments, must possess exceptional wear-resisting properties. This is paramount for ensuring a long operational life, preventing premature material degradation from the constant friction and sliding contact.
Makes sense. Alignment.
Proper alignment. This is non-negotiable. Gears must be aligned perfectly within their housing. Any misalignment, even slight, can lead to uneven load distribution across the teeth, dramatically increased wear, excessive noise, and ultimately premature failure.
Critical.
Very. Also, resistance to tooth deflection, acceleration, and stress concentration. Teeth need to be rigid enough to resist excessive bending or deflection under load, which could lead to imprecise motion. They must also be robustly designed to handle rapid changes in speed and to minimize areas where stress might concentrate.
Weak points.
Exactly. Those invisible hot spots that could initiate fatigue failure over time. And finally, proper lubrication.
Like with belts.
Just as crucial, yes. Adequate and continuous lubrication of meshing gears is absolutely essential. It not only reduces friction and wear, but also plays a vital role in dissipating heat generated during operation, significantly extending the life and efficiency of the gear set.
Okay. That's a lot to consider just for gears.
Yeah.
Now, what about the different types? You said they're classified by tooth shape and orientation.
Yeah, that's right. Let's explore the vast and fascinating types of gears. First, spur gear.
The most common one.
Arguably, yes. Found in everything from wristwatches to car transmissions. Spur gears have straight teeth that are cut parallel to the axis of the shaft. They are exclusively used for transmitting power and motion between two parallel shafts.
Advantages?
Their design boasts very high efficiency with excellent precision, and a critical advantage is that no axial forces are generated between meshing spur gears, which simplifies bearing design.
Okay. Next.
Helical gear. These gears are also used to transmit power between parallel shafts, but with a significant difference. In helical gears, the teeth are inclined to the axis of the shaft, forming a helix, much like a screw thread.
What's the benefit of the angle?
This helical form allows for a larger contact area between meshing teeth, enabling them to handle comparatively higher loads at higher speeds compared to spur gears. This also results in a smoother and notably quieter operation.
Downside.
The trade-off, however, is that these angled teeth impose both radial loads and axial thrust loads on their bearings, which must be accounted for in the design.
I see. What about double helical?
Double helical gear, or herringbone gear. These ingenious gears are essentially two helical gears joined side by side, but with opposing helix angles. Sometimes there's a small gap between them. They are also used for parallel shafts.
What's the point of the opposing angles?
The brilliance of their design is that the two opposing axial thrusts created by the helical teeth cancel each other out, making the shaft effectively free from axial force, thus reducing bearing stress.
Lover.
They offer very high load capacity and smooth operation, but are inherently costlier to manufacture. You typically find them in heavy industrial machinery like large cement mills and crushing equipment.
Okay. Internal gears.
Internal gear. In these unique gears, annular, ring-shaped wheels have teeth on their inner periphery. This design allows for a remarkably compact machine layout, particularly for systems with parallel shafts.
They run in the same direction.
A key characteristic is that the smaller gear, or pinion, meshes with the internal gear, and both run in the same direction. They are incredibly useful for high-load, high-speed applications, offering very high reduction ratios. You'll find them in sophisticated automatic transmissions, cement mills, and wind turbines.
Interesting. What about rack and pinion?
Rack and pinion. This is a fascinating gear system primarily designed to convert rotary motion into linear translatory motion and vice versa. The rack is essentially a gear in the form of a straight bar.
Like a gear straightened out.
You could think of it that way, yes. A segment of a gear with an infinite diameter containing teeth that can be either spur or helical. The pinion is a standard circular gear that meshes with the straight rack.
Where are these used?
Widely used as a precision transfer mechanism in machine tools, printing presses, and robotics, where precise linear movement is required from a rotational input.
Okay. Now for gears connecting shafts that aren't parallel.
Right. First, straight bevel gear. These gears are used to transmit power between two shafts that intersect each other, typically at a 90-degree angle. They are conical in shape and their teeth are tapered.
Designed in pairs.
Yes, designed in pairs and generally not interchangeable. They can operate under high speeds and handle substantial loads, offering good precision. They are notably suitable for use as differential gears in vehicles.
What about spiral bevel gears?
Spiral bevel gear, also used for transmitting power between intersecting shafts. Spiral bevel gears distinguish themselves with curved and oblique teeth.
Curved teeth.
Yes. This specific design provides a larger contact surface between meshing teeth compared to straight bevel gears, resulting in a higher contact ratio, superior strength, and enhanced durability. They are very commonly used in automobiles, tractors, and other vehicles, often for the main drive axles.
Okay. Worm gears.
Worm gear. A worm gear system is designed to transmit motion and power between two shafts that are at 90 degrees from each other and lie on a different plane, meaning they don't intersect.
Like a screw meshing with a gear.
It consists of a worm, which closely resembles a screw, and a mating gear, which is usually a helical gear. This combination is renowned for providing exceptionally quiet and smooth meshing action, and it's often used in applications requiring very high-speed reduction in a compact space, like in tuning mechanisms or lifting equipment.
And spiral gears?
Finally, spiral gear. These gears are specifically used to transmit power between two non-intersecting, non-parallel shafts. They can function as either speed increasers or speed reducers. However, a key characteristic is that they exhibit a significant amount of sliding movement between their teeth during operation, leading to larger frictional losses.
Less efficient.
Generally less efficient than other gear types for high-power transmission, yes.
Wow, that's a huge variety of gears. So with all these complex types, how do engineers precisely define and communicate their dimensions? There must be specific terms.
Oh, absolutely. There's a specific language or nomenclature used to describe the geometry of gears. Let's look at a few crucial terms for spur gears first, as they form the foundation.
Okay, pitch circle.
The pitch circle is perhaps the most important imaginary circle on a gear. Think of it as the theoretical center where the gears effectively mesh, like two smooth, rolling cylinders. The distance between corresponding sides of adjacent teeth, when measured along the arc of this circle, defines the fundamental spacing.
Got it. And circular pitch.
Circular pitch, PC, is the distance measured along the circumference of that pitch circle from a point on one tooth to the corresponding point on the adjacent tooth. It essentially tells you the spacing of the teeth around the gear.
Module. You hear that a lot.
Module M is a very common term, especially in metric systems. It's defined as the ratio of the pitch circle diameter to the number of teeth. So if a gear has a 100 millimeter pitch diameter and 20 teeth, its module is 5 millimeter. It effectively defines the size of the gear tooth. A larger module means larger, coarser teeth.
Okay. Addendum and addendum.
Addendum is the radial distance from the pitch circle to the very top of the tooth. It's the portion of the tooth that extends outward. The addendum is the radial distance from the pitch circle to the very bottom of the tooth, extending inward. These two define the working depth of the teeth.
And clearance.
Clearance is a small but critical amount by which the addendum of one gear slightly exceeds the addendum of its mating gear. This tiny gap ensures that the tip of one tooth never bottoms out in the root of the other gear, preventing interference, undue friction, and allowing for lubrication.
Crucial little gap.
Okay, what about bevel gears? Different terms there.
Now, bevel gears have a different conical geometry, so their nomenclature also shifts to reflect that. We won't go through every single term, but some key ones are the pitch cone.
Instead of a pitch circle.
Exactly. It's an imaginary cone that contains the theoretical meshing line of the teeth. It's the fundamental conical surface upon which the teeth are formed, allowing for power transmission at an angle.
Cone center. The cone center is the apex of this pitch cone. This is a crucial point where the axes of the two mating bevel gears intersect each other, which is fundamental to how these gears operate.
Pitch angle.
The pitch angle is the angle made by the pitch line of the axis of the shaft. It essentially defines the slope of the pitch cone, dictating the angle at which the gears will mesh.
And face angle and root angle.
And the face angle is the angle defining the top surface of the tooth, while the root angle defines the angle of the bottom surface. These, along with other terms, meticulously define the complex tapered shape of a bevel gear tooth, ensuring precise and strong engagement.
Wow, that's an incredible amount of specific terminology, but it absolutely highlights the incredible precision and thought required in engineering these components. It's not just about getting the teeth to line up.
Not at all.
It's about making sure they work efficiently and last. Okay, let's shift our focus now to one of the most common and arguably complex machines we interact with every single day. The internal combustion engine.
Ah, the IC engine.
A classic. So what exactly is an internal combustion engine? At its heart.
It's an engine where the combustion, that is, the rapid burning of a fuel, takes place directly with air, which acts as the oxidizer, inside a highly confined combustion chamber or cylinder.
Inside the engine itself.
Correct. Internal combustion. The real magic unfolds as this combustion converts the chemical energy stored in the fuel into raw thermal energy, which then dramatically increases the temperature and pressure of the gases within that chamber.
Creating high pressure.
Extremely high pressure. The expansion of these superheated high-pressure gases then applies a direct, powerful force to the engine's components, typically pushing a piston or spinning a turbine. This force, moving the piston over a distance, is precisely how the chemical energy of the fuel is ultimately transformed into usable mechanical energy.
That drives your car, powers a generator, or makes a lawnmower cut grass.
Exactly.
Now, you mentioned fuel type and ignition method to find the engine type.
What's truly fascinating here is how the type of fuel used and the method of ignition fundamentally define the engine type and its operational characteristics. Internal combustion engines are broadly classified into two primary categories. First, we have spark ignition, SI engines.
Petrol engines.
Right. These are the engines that predominantly use petrol or gasoline as their fuel. In SI engines, a precisely proportioned mixture of petrol and air, typically prepared in a carburetor in older engines, or more commonly via sophisticated fuel injection systems in modern ones, is drawn into the combustion chamber.
Then the spark plug ignites it.
Correct. Once inside, this air-fuel mixture is then ignited by means of a spark plug, which delivers a high-voltage electrical discharge between its two electrodes, creating that critical spark that initiates combustion.
And there are two-stroke and four-stroke versions.
Yes. The operating cycle of an SI engine can be completed in one of two ways. Two-stroke engines, as their name implies, complete one full cycle in just two strokes of the piston, which corresponds to one crankshaft revolution. They are known for their simplicity, lightweight design.
Found in smaller things like scooters, chainsaws.
Typically, yes.
Yeah.
Light vehicles, small power tools. Then there are four-stroke engines. These are the workhorses of most modern vehicles. They require four distinct strokes: intake, compression, power, and exhaust to complete one full cycle, which spans over two complete revolutions of the crankshaft.
Motorcycles, cars.
Found in most modern motorcycles, cars, and other passenger vehicles, offering better fuel efficiency, lower emissions, and generally smoother operation than two-stroke engines.
Okay. And the other main category.
The second major category is compression ignition, CI engines, which use diesel as their fuel. The operating principle here is distinctly different.
How so?
In CI engines, only pure air is supplied to the combustion chamber. This air is then compressed to an incredibly high pressure. This compression dramatically raises its temperature, typically to somewhere between 600 to 1,000 degrees Celsius.
Hot enough to ignite fuel just from the heat.
Exactly. Hot enough to ignite fuel on contact. At this incredibly high pressure and temperature, a very fine spray of diesel fuel is then injected directly into the superheated compressed air. The diesel fuel immediately ignites spontaneously upon contact with this hot air without the need for a spark plug.
Auto ignition.
Precisely. It's like a controlled explosion just from the heat, no spark needed.
Okay, so SI uses the spark, CI uses compression heat, but they share core components.
Yes. Regardless of their fuel type or ignition method, all internal combustion engines share a set of core components that work in incredibly close harmony to produce power. The main parts universally include the cylinder and cylinder liner,
where combustion happens.
Right. The piston, piston rings, and piston pin, the dynamic components moving inside. The connecting rod.
Linking piston to crankshaft.
Correct. The crank, crankshaft, and crank pin converting linear to rotary motion. And the valve gear mechanism.
Controlling intake and exhaust.
Exactly. Each of these parts is meticulously designed to withstand extreme conditions, tremendous pressures, high temperatures, constant motion, and to perform its specific function flawlessly.
Okay, let's break these down one by one.
Okay.
Start with the engine cylinder, the heart of the combustion process.
Right. The cylinder is truly the central working part, the core chamber where that intense combustion takes place. It's generally a single piece, robust casting, typically made of durable materials like cast iron or aluminum alloys.
Chosen for strength and heat resistance.
Exactly. These materials are chosen specifically for their exceptional strength and their ability to withstand the incredibly high temperatures and pressures. The piston travels precisely up and down within the confined space inside the cylinder.
What's its main function?
Its fundamental function is twofold. First, it's designed to reliably contain the working fluid or fuel mixture during the combustion cycle, ensuring pressure is contained. Second, it precisely guides the motion of the piston, maintaining a perfectly straight path.
And engines can have multiple cylinders.
Right. In multi-cylinder engines, they're typically arranged side by side within a larger solid engine block.
What about the liner or sleeve? Why is that needed?
The cylinder sleeve or liner, crucial for durability. You see, the inner wall of the cylinder is subjected to incredibly high temperatures, immense pressures, and constant friction from the piston. This leads to wear.
So the liner is replaceable.
Exactly. To prevent replacing the entire expensive engine block when the wall wears out, the cylinder is equipped with these replaceable sleeves or liners, typically made of incredibly wear-resistant iron alloys.
What does a liner actually do?
It serves several vital functions. It acts as the interior wall, providing a smooth, hard-wearing sliding surface for the piston. It efficiently transmits combustion heat to the coolant system, preventing overheating, and it's essential in preventing high-pressure gases from escaping.
Are there different types of liners?
Yes, two main types. Dry liners, which don't directly touch the cooling water heat transfers through the block material, and wet liners, where the outer surface does have direct contact with the cooling water.
Wet liners cool better.
Often more efficient heat transfer, yes, but they need more careful sealing at the top and bottom to prevent coolant leaks.
Okay. Now, moving inside the cylinder, the piston and piston rings.
Right, inextricably linked to the cylinder. The piston is a reciprocating component, moving back and forth within the cylinder. Its primary function is to transmit the immense force from gas expansion to the crankshaft via the connecting rod.
Translating heat energy to motion.
Exactly. Beyond this, it also dissipates heat to the cylinder walls and, crucially, seals the cylinder from the crankcase below, primarily using the piston rings.
What are the parts of a typical piston?
The pistons in IC engines are usually trunk type. They consist of several key parts. The head or crown the top surface facing combustion, shaped variously, flat, convex, concave, for combustion chamber design. Piston rings, absolutely crucial for sealing and heat transfer. The skirt, the lower part, bearing side thrust against cylinder walls. And the piston pin, or gudgeon or wrist pin, connecting the piston to the connecting rod.
What are the main design challenges for a piston?
When designing a piston, engineers must balance critical factors. It needs high strength for gas pressure and inertia forces. It should have less weight to minimize inertia forces for higher speeds.
Strong but light.
Exactly. It must reciprocate at high speeds without noise. It needs to quickly disperse heat to cylinder walls. It must form an effective seal against gas and oil leakage. It needs sufficient bearing area on the skirt to prevent wear. It should have little corrosion tendency. And finally, sufficient rigidity to withstand thermal and mechanical distortion.
That's a demanding list. Now tell us more about the piston rings.
Piston rings are truly engineering marvels. They are typically made from cast iron and its alloys, chosen for excellent wearing qualities and retaining springiness at high temperatures.
Special materials for high performance.
For very high output engines, yes, heat-treated high-carbon cast alloy with nickel, chromium, molybdenum for superior strength. Frequently, they're chrome-plated to reduce wear on the cylinder liner.
What are the different types of rings?
Two primary types. Compression or pressure rings. These are inserted in grooves in the top portion of the piston, usually 2 to 5 rings. Their main functions are transferring heat from the piston to the liner, and most importantly, sealing the combustion gases within the cylinder.
How do they seal?
They're made slightly larger than the cylinder bore, then cut, creating a gap. This allows insertion and provides outward spring pressure against the cylinder wall for sealing.
And the other type? Oil control rings.
Yes, oil control rings or oil scrapers, located below the compression rings. They often have a channel and slots. Their job is twofold. Allow sufficient oil upward for liner lubrication, but critically scrape excess oil off the liner during the downward stroke.
To stop it burning in the combustion chamber.
Exactly. Minimizing oil flow into the combustion chamber, which reduces emissions, carbon deposits, and oil consumption. They manage the oil film meticulously.
Critical detail. Okay, next component. The connecting rod. The link between piston and crankshaft.
This is truly the crucial link that translates the piston's up and down reciprocating motion into the continuous rotational motion of the crankshaft.
What's its primary function?
It acts as that essential intermediate link. It's connected to the piston by the piston pin, and its fundamental function is to transform the piston's motion into rotary motion through the crank, transmitting both the push and pull to the crank pin.
Any secondary functions?
In many engines, yes. It often conveys lubricating oil from the crank pin up to the piston pin, ensuring lubrication, and it sometimes splashes oil for cooling the underside of the piston crown.
What are its main parts?
A typical connecting rod has three main parts in its composition: a small end, a big end, and a long shank. The small end is eye-shaped, usually with a phosphor bronze bush, connected to the piston by the pin.
And the big end?
The big end is typically split into two halves, allowing assembly around the crank pin, fastened with clamping bolts. The shank connects the two ends, often drilled for oil flow.
What are the bearings?
The big end bearings are typically multi-layered: steel, brass, bronze with white metal lining, usually splash lubricated. The small end bearing is often pressure lubricated via oil pumped through the rod.
Design considerations for the rod itself must be strong.
Very high demands. It must have ample strength for gas pressure and inertia. It should be lightweight to minimize inertia forces. It's primarily considered a strut compression member for design against buckling. And it must be robust enough for bending stresses, especially at high speeds.
What forces act on it?
The acting forces are complex. The main force from gas pressure inertia of reciprocating parts, the inertia of the connecting rod itself, and frictional forces from the piston rings and the pin bearings. All must be accounted for.
Okay, that leads us finally to the crankshaft, the backbone of the engine.
Truly the very backbone of the engine's mechanical operation. The crankshaft is a robust rotating component connected to the crank mechanism. Its main function is converting the piston's reciprocating motion into continuous rotatory motion.
And delivering power out.
Exactly. It's the central recipient of all power produced by the pistons, delivering it to the transmission system, typically via a flywheel to the clutch.
What's its composition? It looks complex.
It is intricate. It features crank pins, one per cylinder, where the connecting rod's big end attaches. These pins are eccentric to the crankshaft axis. This arrangement forms the crank throws, dictating piston stroke.
What supports the crankshaft?
Robust main journal bearings support the crankshaft, allowing smooth rotation and sustaining axial radial loads. It also has substantial crank arms, or webs, connecting crank pins to main journals, preventing bending from centrifugal force.
And counterweights.
Crucially, counterweights are strategically provided. These balance the reciprocating mass of the piston and connecting rod, improving smoothness and reducing vibration.
How does it connect to the camshaft?
Via various timing systems, timing gears, sprockets, or chains, ensuring precise synchronization of valves and ignition.
Are there different types of crankshaft?
Yes, based on two criteria: by position of crank, side overhung, crank pin outside main bearings, or center crankshaft, crank pin between main bearings, and by number of cranks, single throw, one crank for single cylinder, or multi-throw, multiple cranks, for multi-cylinder engines.
And the design demands must be huge.
Incredibly high design considerations. It must be strong enough for bending, twisting moments, and rigid enough to minimize distortion. Mass distribution is critical to keep natural vibration frequency away from operating speed, avoiding resonance.
Prone to failure.
They're constantly subjected to fluctuating bending and shear stresses. Failure often occurs via progressive fractures due to repeated bending or torsional stresses, fatigue failure. Therefore, it must be exceptionally strong and rigid, also damping vibration.
And avoid sharp corners.
Finally, yes, abrupt changes in cross-section must be rigorously avoided. These create stress concentrations, common fatigue failure points. Smooth transitions and generous fillets are key for longevity.
What an incredible journey we've taken today through the intricate world of machine design. We've explored its very essence, from broad definitions and classifications to the elegant complexities of power transmission systems, and then dove deep into the core components that make an internal combustion engine roar to life.
Quite the tour.
What this all means, really, is that behind every smooth-running machine, every reliable piece of equipment, and every technological marvel that seamlessly simplifies our lives, there's a universe of thoughtful engineering, advanced material science, and incredibly precise calculation.
It's easy to take for granted.
It is. It's a profound testament to human ingenuity, translating complex physics into tangible, functional devices that shape our modern world.
And this raises a fascinating question, doesn't it? Knowing how these individual elements are meticulously designed, how they function, and the vast considerations that go into each one, what new possibilities emerge if we were to rethink their fundamental interactions or combine them in truly novel ways?
Like system-level innovation.
Exactly. Consider for a moment how seemingly minor adjustments, say, a slight tweak in material choice, Or a tiny refinement in the shape of a single component, like that piston ring we discussed, can ripple through an entire system,
Yeah.
dramatically impacting its efficiency, its overall cost, and even the safety of the final product. The principles we've discussed today are the fundamental building blocks of almost everything mechanical around us.
A final thought for our listeners.
As you move through your day, perhaps you can now observe the machines around you with a new set of eyes, recognizing the elegant design decisions and the intricate engineering that often go completely unnoticed, yet silently power our world. Keep that curiosity alive.